All right. Well, good morning, everybody. I'm so happy to be here. My name is Emily Robb, and I will be talking about architectural realities from L2 to higher levels of autonomy. So let's jump in. General outline of the talk today, give a little bit about my background, the background of Stellantis, the products that we have in autonomy. We're going to talk a little bit about centralization and what makes sense to centralize versus what makes sense to keep at the edge. Just an opinion here. And then at the end, we're going to get into scalability from entry to premium autonomy and how that relates to some different perception and planning architectures. Stellantis, we are an automotive OEM with 14 different iconic brands. Most well known here in the US, of course, we've got Ram, Jeep, and Chrysler and Dodge. We do have a L2 Plus system, which is called Hands-Free Active Driving Assist. And it's shown here on our Ram Tungsten. This is a great L2 Plus feature. You can drive hands-free on the highway, and it also offers semi-automated lane change. Thank you for that. That was an introduction to my my resume. So my background, I did my education at the University of Michigan, where I focused on chemical engineering and material science. I did some research in 3.5 semiconductors while I was there. My first foray into the automotive industry was in head-up displays, and then I moved into some research in augmented reality, which is where I got my first taste of ADAS. And it was just in forward cameras, just when that, like ACC and AAB was just getting started. I worked, of course, in that space for a while. And then I moved into a broader role in LiDAR and radar sensor systems engineering. And then I moved into AI, data collection, ground truthing, annotation and labeling, and data management. And now I'm currently a senior fellow at Stellantis, where I focus more on our next generation architectures, looking at a lot at perception and sensing. Okay, software-defined vehicles. There's a lot of talk about them. They're very flexible, they're very high performance, huge amounts of compute we can put in the vehicle. With all of that promise, there's also more organizational complexity. So what is the motivation here? There's a product, a technology platform, I should say, at Stellantis called Stella Brain, which is our SDV platform. So talking a little bit about what is the motivation for centralization. In a decentralized architecture, you have a one-to-one mapping between features and your sensors. So I'm showing here on the left-hand side, you might have an ECU to process all of your interior cameras, whether it be your digital rearview mirror or e-mirrors. You might have an ECU for parking, an ECU for high-speed ADAS. This is an ECU that delivers a specific feature. And the way that traditional OEMs are thinking about it is, I have a feature, I'm going to plug it in, I'm going to integrate it on the bus. We can share data between these ECUs, but it's very high latency and it's only highly processed data, such as object lists, lane lines, classified ultrasonics. If you want to share camera data between different features, you're going to have to either package multiple cameras or you're going to have to pay for high-speed interfacing, LVDS. You also have to pay multiple times for each different ECU in terms of the mechanical, the basic software, the wiring. There's additional networking complexity, bus loading. And there's a big missed opportunity for cross-correlation of raw, high-bandwidth sensor data. And more in the AI space, we're seeing that that's necessary to provide the high levels of feature content that the industry is trending toward. It's also expensive. You're spending more of your BOM on complexity rather than improved sensors and compute, which directly correlates with better customer experience. So, centralized architecture is depicted here. You have an HPC composed of maybe one or many multi-core SoCs, each of which has neural processing, graphics, CPU, image signal processing. You could have up to 20 to 30 gigabits per second of camera data going in and being shared between multiple different sensor-consuming applications. Ultrasonics, 1 to 2 megabits per second. You can get envelope interface with that. You can get raw interface with that. And then on the radar side of things, right? In the past, you would be able to share object lists. now, you can bring detections in over Ethernet, 60 megabits per second. There's even trends in the future towards bringing raw 1D FFT or even more raw data for cross-correlation. So here's a case study for why a centralized compute system would bring flexibility. So imagine you're developing your decentralized architecture. You've built your architecture around the software architecture. So your electrical architecture has an ECU for each feature. All of your sensors that are delivering that feature are connected to that specific ECU, and all of those ECUs are communicating on the bus. So we've got parking ECU, we've got a smart camera, we've got an ultrasonics ECU with classified ultrasonic detections going to the parking ECU, and so on. It's all good at SOP -4. Call your attention to one more thing. There's a green line at the bottom where we have a processing flow, starting with single sensor perception, followed by sensor fusion, localization, planning, and motion control. Just an abstracted view of an ADAS processing flow. That green line is showing where the bus interface is and where that sensor data is then available to other ECUs. So suddenly, at 1 year before SOP, a disruptive technology appears. This is from the Attention is All You Need paper. It's a transformer. Made a big splash over the past 3 years in LLMs, as we all know. It's also making a splash in automated driving. We'd like to be able to use it in the vehicles, but the architecture that we had before didn't support it. We needed high bandwidth video interfaces, maybe even radar high bandwidth interfaces. And we need a different compute platform. We need a large and more powerful SoC, perhaps with graphics or neural network accelerating. The green line, you can also see that it's moved to the right? A big reason for these architectures being so much more performant is just the fact that all of that information from those sensors, as it's being processed, it's flowing through the decision-making pipeline until much, much later in the pipeline. And so the AI system is deciding what to keep and what to throw away, rather than a human deciding that we're going to represent the environment as objects and lanes and free space and so on. So I think I'd like to say that I made the case for high feature content, but I'd say that SDV also exists with regulatory feature content as well. Taking a look at the FMVSS 127 included child scenario, which I think gives many people heartburn in this audience. It gives me heartburn. Looking at the time to collision, right? So in this scenario, there's a pedestrian on the side of the road behind two parked cars. The pedestrian starts to move at 2.8 seconds, but it's 1.44 seconds TTC, or time to collision, when the pedestrian is no longer occluded. So if you're relying on a sensing system that needs to have line of sight, you only have 1.44 seconds. So there's multiple different speeds in this regulation, from 10 to 50 kph. And what this chart is showing is the acceleration that would need to be reached for an ideal deceleration profile, which is not physically possible, but just as a thought experiment, right? So if you immediately are able to reach your maximum deceleration at 1.44 seconds TTC, you'd have to reach almost 1 g of braking at that 50 kph initial subject vehicle velocity. That's a lot. It's achievable, but it's a lot. And it's in an ideal condition. We're talking no system latency, no brake build time, and ideal friction conditions, which that's the test case for the regulation, but it's also not realistic for the real world. It starts to get even worse when you consider the latency stack up. So thinking of a late fusion architecture, you've got a camera, which typically takes 1 to 3 frames to produce a track, a camera CNN, or a radar tracker, which typically takes 3 to 5 frames. The long pole in the tent is the radar. You could be up to 250 milliseconds right there. Sensor fusion, let's say you take a frame, another 50. The planning logic, 10 to 40 milliseconds, and then 250 milliseconds for brake build. I know these numbers are, it really depends on the technology, what these numbers exactly are. Sometimes you can do better here. But just looking at this, right? You could have between 210 to 340 milliseconds, followed by brake build, which means that braking starts at between 1.1 and 1.23 seconds TTC. Well, if you look at the braking decel profile of -10 meters per second squared, your time is 1.7 seconds. That's more than that 1.44 seconds, which is a fail right away. And then in a low mu scenario where your max decel is -6.8 meters per second squared, it's a time of 2.3 seconds. So you also failed. So what are your options? Since both are greater than 1.44 seconds, you can either reduce the latency or you could leverage partial queues. So another aspect of the FMVSS 127 regulation that would benefit from centralization is this low-speed occluded child scenario. The 10 kilometer per hour scenario results in pedestrian reveal at very low range, which means that adding that fisheye camera or a lower sensor, maybe a radar even, a dual sensor approach is required for this scenario on some vehicles. So looking at this, in your decentralized architecture, you have a couple of options. None of them are really good. You can break on a single sensor camera. You can break on a single sensor radar. But either way, you're throwing out data from the other sensor. You're reducing your confidence, you're reducing your robustness, and you're choosing between poor pedestrian classification performance or a poor motion estimate, neither of which are ideal. And then if you want to share data, you also have to deal with the network latency as well. If you're in a centralized system, you can leverage partial queues from your additional sensors. For example, a thermal camera or even a radar. You could get some signature from that pedestrian before it comes out from behind the vehicle. The other thing you can do is leverage an early multi-sensor fusion architecture. So instead of following the detect, tract, fuse, predict path, you could have a single fused inference in basically one frame, reducing your latency. And you already have all of your sensor data networked in, so you can use whatever you want without having to make a network architecture change. That being said, centralization is a trend, but not everything makes sense to centralize. So here's a graphic showing one opinion, my opinion, of what makes sense to centralize versus not. The green arrows are showing things that we've already discussed, like shared raw data access, early sensor fusion, bird's eye view perception, shared world model between multiple different apps. High performance is required, high compute needs. But it still may not make sense to centralize features like passive entry, child presence detection, or security features, or even just standalone driver monitoring, if it's just a single sensor with a single driver monitoring output. So taking a little bit of a closer look at a few different architectures for the low power security features. So we're going to look at centralized low power, and edge low power. So at the very top, the centralized architecture has an edge sensor, which is operating in normal conditions. You have sensor data capture, could be an image sensor. You have a transmission IC. And then you have the HPC, which is also operating in full power mode. So you have the receiver, all your signal processing, your NPU processing your AI, your recording, all that's full power. So looking down to just an idea of what that power draw would be, you could have 2 to 5 watts for an individual sensor. I'm not talking about the entire sensor system because that would be even more, right? But like an individual camera, and then 30 to 50 watts on the HPC. That results in the time to drain the battery between 8 and 14 hours. Another option that you can do is run your HPC in low power mode. So that means that some of the cores in the HPC are awake, but some of them are still in a low power mode. So that the sensor is completely operating in full power mode. And then once the HPC detects an event, then it would wake up the rest of the cores of the HPC to manage the recording and the streaming functionality. That is a little bit better on time to drain the battery, between 1 to 3 days. Then you have these edge low power architectures, which are much, much better on power consumption. So this architecture is a little bit different because you're actually moving that signal processing, the neural network processing, and the memory buffer from the HPC to the edge. And there's various different architectures and designs out there. This is a more generalized view of just shifting that functional allocation to the edge. And then what happens is your HPC is in a low power mode. If the edge sensor detects something, an event, then it would wake up the HPC via the edge and then trigger more advanced detection, maybe a confirmation, and then streaming or an alert. And that time to drain the battery is between 7 and 45 days, according to my estimate here. So I think this is clearly making a case that not everything is going to be centralized. Just a little caveat here on these estimates. These numbers are probably overestimates for how long it would take to drain the battery. It's going to be a lot less just because the HPC is going to be waking up and going into remote service mode. You're going to be, starting the car multiple times, maybe, hundreds of cold cranking amps anyway each time, not charging the battery fully every time. So this is just a comparative activity. All right, the last topic here is scalability. So this one I think is very interesting because we're moving into the space of very large monolithic AI models, and they're having an extremely good performance at the high end of autonomy in the L2++ and L3 space. The structure for these models is typically you have multiple different sensor inputs that go into an encoder. They go through a backbone, multiple different architectures here, of course. And then there may be multiple different prediction heads. This is, I think, a trend where the industry is going on the high end, but however, it doesn't scale down easily to entry. So that's what we're going to be talking about is if you want to leverage the performance of these types of AI models, what are your scalability options across the vehicle portfolio and how do they compare to each other? So we're going to be looking at 4 different options. The first option is a modular software architecture where you add software components for each new feature content incrementally, and you add sensors at each level incrementally too. The premium stack is dependent on entry software. So if you were to remove the entry stack from the premium vehicle, the premium software wouldn't run. This is kind of an older approach, not seen as much anymore, but it has its fans because of the efficiency in the compute footprint. The second option we're going to look at is you actually run a parallel entry and premium software stack together on your premium vehicles. This preserves the validated entry architecture, and it allows you to implement a premium end-to-end AI model in your premium vehicles and achieve that performance gain. The last 2 options, you actually do have different entry and premium software architectures, so you do not preserve that validation on the premium vehicles. Option 3A uses the classical approach on entry and the end-to-end AI approach on premium. 3B uses the end-to-end AI approach on both premium and entry, but it uses a distilled version of the premium model on entry. So taking just a little bit deeper look at an abstracted view of option 1, which is the modular stack. We're showing on the left side the premium vehicle and on the right side the entry vehicle. You can see that the entry vehicle architecture is a more classic software architecture flow. So you've got front cameras and radars, each of which is going into a single sensor perception. For radars, it'll be a tracker. For front cameras, it'll be a CNN. And then a classical sensor fusion, common filter type, and then your traditional planning feature logic to deliver your entry features, AB, ACC, lane control, L2, entry stuff. You keep that when you go to the premium vehicle. And the difference is that the add-on software components for the premium vehicle leverage the single sensor perception from the entry vehicle. So there's still individual CNNs for all of your premium sensors, and the sensor fusion block incorporates the entry CNNs. Number 2, the parallel entry stack. So the blue premium stack is completely independent. It has additional sensors compared to entry. So you can see there's add-on cameras, add-on radars, maybe even a LiDAR. And then it goes directly into a vision language action model or end-to-end AI. The place at which it intersects with the regulatory stack is at the very beginning of the flow. So the front camera and the radar data, as soon as it gets into the HPC, it gets split and it goes into both software architectures at the same time. You run them in parallel, and then you arbitrate at the end, deciding which one actually goes to motion control. Number 3, you actually have 2 separate stacks. So the difference here is you have an end-to-end AI model on premium that incorporates the entry feature content. And so you can see here, there's a note next to the VLAN backbone that says the learned features here. Entry features, highway for in-lane ODD, as well as premium features, including the urban ODD, like the pedestrians, cyclists, intersections, traffic lights, and so on. And then it also has the learned behaviors corresponding to both entry and premium. So again, the learned behaviors would be A, B, lane control, L2, and the premium behaviors would be the urban behaviors. All right, and then the last option is, it's the same thing on premium, but then on entry, you can see the difference is the features and the behaviors are a subset of the premium features and behaviors. And so this might be the same model architecture. It might be the same data set, but only using the entry ODD and the entry scenarios, but maybe the same annotation and labeling tactics, and the same behavioral output. That would have to be enforced. It wouldn't be architected, it would be enforced by the training and the validation process. So just a brief note on model compression tactics and distillation. Quantization and pruning are not technically distillation, so I broke them out separately, but quantization is very commonly used. It's reducing the resolution of the weights, for example, from floating point 16 to int4. Pruning is reducing the number of connections between neurons. Both of these can reduce the size of the network and make it portable to a smaller compute. And then distillation is something a little bit different, where the teacher model is very large, and it also has an inductive bias, right? It has a reasoning behind the decisions that it makes. And you're transferring that inductive bias to the student using soft labels. So as an example, you can kind of see every prediction head may be associated with a probability distribution. And the ground truth would have 100% that histogram across all of those classes, right? Well, the correct class would be 100%. That's that green bar graph on the bottom with the X through it. That's what you train the teacher on. The teacher itself, for every sample of data, it has a probability distribution. It's still correct with respect to the ground truth. The highest probability bin is still number 5, just like the ground truth. But it also tells you which of the classes it thought were kind of similar. And so you train the student on that soft label, on that probability distribution, instead of the ground truth. And there's many other ways to do this as well, going deeper into the model. Very hot area of research, but that's kind of the concept. And so just a final note on this. Skip this slide. I did something that you should never do when you're doing a presentation. I made a slide with a lot of words on it. So I apologize for that, but I'm going to go through and compare these. Okay, so number 1, modular software architecture. The big con is that your premium feature content is just never going to be competitive if you do this. It is not state of the art. However, a pro is it's compute efficient, it minimizes revalidation for entry, and it's explainable. Number 2, parallel entry and premium stacks. It has the same pros as option 1, but your premium feature content is no longer bounded. And it has an additional benefit where your premium feature improvement is decoupled from regulatory risk. So it's very interesting from that standpoint. You do have architectural duplication. You do have compute increase beyond what you would have if you didn't run them in parallel. And your entry content on premium vehicles is performance bounded. 3A, the premium features are just like 2, they benefit. The entry features on premium vehicles benefit as well. So that's the big difference is you have an end-to-end AI model that has incorporated all of your entry feature content as well. The problem is you have unique validation for full feature content per trim. You have to validate entry twice and potentially homologate it twice, which is very expensive. And then the last one, 3B, you have an end-to-end AI model for both. Your entry and your premium vehicles can share training lineage, data, and behavioral intent. And you still have the significant con where there's a unique validation for full feature content per trim. Also, because you don't have all of your premium sensors on entry, you may have behavioral differences between entry feature content on premium and trim. So you may actually have 3 different stacks potentially to validate. But I think this is where I want to pose a thought question. If future AD systems adopt a VLAM-style architecture, which portions do we think could be shared across trims and software generations, and which portions must be independently validated? So, thank you very much.
Thank you very much. Thank you very much. Are there any questions from the audience? We probably have time for 1 or 2 questions.
Great presentation, Emily. So I have a question that, for example, when we are doing the hybrid approach, that model 3B, using the VLA model would be very expensive for entry variant because, where you will be doing a lot of end-to-end AI modeling, you need high-powered processing capability. So how do we mitigate that? Because for the entry, one of the key reasons that we are still stick with the modular approach is primarily because of the cost, and we cannot afford to have high-powered compute power for the VLA model to execute it. So I don't know, how do we have this collaboration between entry and the last 3B version of it?
Yeah, you're basically talking about compute power. You'd have to have better compute on entry than you'd have today, and you'd have to have a probably centralized style architecture with a big NPU or a decent sized GPU.
I see. Okay, thank you.
Emily, thank you very much for your very encouraging and good presentation and the insights from Stellantis. Thank you very much.
Thank you very much.